We show that differentiable simulation offers considerable advantages over model-free reinforcement learning for policy training in legged locomotion. Notably, we demonstrate that a single robot, without the need for parallelization, can quickly learn to walk within minutes using our approach. We design a simple velocity tracking task where the robot is required to follow a constant velocity in the x-axis with a linear velocity equal to 0.2 meters per second. Each iteration, we simulated 24 time steps with one single robot. Hence, each training iteration contains only 24 data points. We trained the policy for a total of 1,000 iterations. Surprisingly, despite extremely limited data, our policy successfully learns to walk after minutes of training. Though our approach enables tracking a constant velocity using one simulated robot on flat ground, it is generally helpful to parallelize the simulation for more complex tasks. To this end, we design a more difficult task, learning diverse locomotion skills over challenging terrains. Specifically, we design 4 different gait patterns, including trot, pace, bound, and gallop. Additionally, we vary the gait frequency from 1 Hz to 4 Hz. The robot receives a high-level velocity command and is required to track randomly commanded velocity. We show that when augmented with GPU parallelization, our approach allows the quadruped robot to master diverse locomotion skills, including trot, pace, bound, and gallop, on challenging terrains in minutes. While model-free reinforcement learning can also achieve similar performance given sufficient parallelization, our approach requires significantly less data. In this task, we only need roughly 64 robots to achieve stable policy training. Finally, we show that the policy trained via differentiable simulation can be transferred to the real world directly without fine-tuning. For the first time in robotics, we demonstrated using differentiable simulation to control a real quadruped robot. This highlights the potential of differentiable simulation for real-world applications in dynamic legged locomotion scenarios.
Try kick.
The key to our approach is a novel policy training framework that combines the smooth gradients obtained from a simplified dynamics model for efficient back-propagation with the high fidelity of a more complex, non-differentiable simulator for accurate forward simulation. First, rather than handling the whole body dynamics as a unified differentiable simulator, which may encounter non-smoothness due to contact interactions, we propose to separate the simulation into 2 distinct spaces, the floating base space and the joint space. For the robot body, we employ an approximation using single rigid body dynamics, which offers a continuous and effective representation of the main body. The simulation within the joint space benefits from the inherent differentiability and smoothness of a proportional derivative PD controller. This allows us to treat the PD control as an explicit, differentiable layer within our simulation framework. Second, to address potential inaccuracies arising from our simplified rigid body dynamics model, we incorporate a more precise, non-differentiable simulator. This non-differentiable simulator can simulate complex contact dynamics and is used to align our simplified model, thereby ensuring that our training pipeline remains grounded in realistic dynamics. Third, instead of directly solving a long-horizon policy training problem, We utilize short horizon policy learning to achieve stable gradient backpropagation over a short horizon.